Hey, my name is Harshita, and this is your Belmont Math Science Center tutor tip. Sometimes students have trouble memorizing the different types of chemical bonds and intermolecular forces and how to distinguish between them. In this video, I will go over some of the major bonds and forces we come across in chemistry classes, and also talk through multiple examples which will potentially clear up some of this confusion. So starting off, these are the forces that I will be talking about in this video. So these can be divided into two types. There's intramolecular forces and intermolecular forces. Intramolecular forces are the chemical bonds that we kind of draw out in structures. So there's two types in that, the ionic bonds and covalent bonds. And intermolecular forces are forces that are present between different molecules in any space. So the four that I'll be talking about in this video are IonDipole Forces, hydrogen bonding, DipoleDipole Forces, and London Dispersion Forces. And just so you know, I've listed these bonds and forces in order of strength, so the ones at the top are stronger than the ones at the bottom. So ionic bonding is stronger than covalent bonding. And similarly, ion-dipole forces are stronger than, let's say, dipole-dipole forces. And London dispersion forces are the weakest of all of these. So yeah. So the first one is ionic bonding. So ionic bonds are bonds between a cation and an anion. And in case any of you guys aren't sure what those mean, a cation is basically a positively charged atom or molecule, and an anion is a negatively charged atom or molecule. So a cation can also be called like as a metal, and an anion as a nonmetal. And an easy way to distinguish between what are metals and nonmetals is if you look at the periodic table and you look at the little staircase that you can form from like the top left corner of kind of like that right block-ish, like this little area. So everything that touches these like bolded lines is a metalloid. So everything to the left of it is a metal, and everything to the right of it is a nonmetal. So this diagram has the metals in yellow and the nonmetals in blue. An important thing to remember is aluminum is the one exception in this, because everything has exceptions in chemistry. So aluminum is a metal, which I think isn't that hard to remember because I think a lot of people just know through life experience that aluminum is metal. But in case you didn't know, you know. So anyway, ionic bonds work through electron donation. So you can look at this figure over here with sodium and chlorine. So in this one, sodium is giving off its electron, the yellow dot, to the chlorine atom, so that the outermost shell of each of these atoms is completely filled. So you can see that sodium has 8 little yellow dots, which represent electrons, in its outermost shell. And then same with chlorine, it also has 8 little dots, even though they're not the same color, it doesn't matter because they're all electrons. So they're all completely filled, so that's a sign of ionic bonding. And again, you can see that this is a positively charged and a negatively charged atoms coming together. So another example is with MgCl2, where the magnesium is giving, it has two kind of like spare electrons in its outer shell that it would like to give away. So it just bonds with 2 chlorine atoms and gives each of them one electron, so that the outermost shell of both of the chlorines and the outermost shell of the magnesium are completely filled. And again, this one is positively charged and these are negatively charged. So then we come to this diagram, and this was just an example of how like an anion doesn't just have to be like an atom, it can be, or even a cation, it could be like a polyatomic molecule. So I have phosphate over here, which is negatively charged, and then there's 3 potassium ions that are sharing their electrons to make this potassium and phosphate compound. So the next one is covalent bonding. So covalent bonding is bonds between 2 or more anions, and again, anions are just negatively charged atoms or molecules. So covalent bonding is based on electron sharing. So what happens is, instead of giving an electron away to the other atom, like as happens in ionic bonding, they kind of like say, let's share it, and so that we're both happy. So in this example, there's atom A and atom B, where both of them are nonmetals, or there's non-metal and a metal right here. So they both need one more electron in their outermost shell to kind of have that filled state. So if either of them give one away, then one of them will be filled and the other one's just going to need 2 now instead of just 1. So instead of that, they're sharing it so that in that overlap region, they both have like 8 electrons in their outermost shell. So an example would be CCl4, where carbon, which has 4 valence electrons, is sharing its electrons with 4 chlorine electrons to give this carbon tetrachloride structure. So you can see that the black dots are the carbon's electrons, and the kind of greenish turquoise-ish dots are the chlorine electrons, and you can see how they are, like, if you kind of look at each individual atom, it looks like they all have 8 in their outermost shell. So they're sharing that. And again, more examples, there's water. So the X's are, or the plus signs, or X's or whatever, are electrons of the hydrogen, and the dots are electrons of oxygen. So again, there's sharing going on over here and over here, so that they all have hydrogen has 2 because that's the most it can get for its outermost shell, and oxygen has 8 because that's the most that it can get for its outermost shell. So there's covalent bonding over there. And again, for CO2, carbon dioxide, same thing. The O's are the electrons of carbon, and the X's are the electrons of oxygen. And again, you can see that after covalent sharing, there's 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen, and then same 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen, and 1, 2, 3, 4, 5, 6, 7, 8 for this carbon. So those were our intramolecular forces. And intermolecular forces, we're going to move on to IonDipole Forces, which is like the attraction between an ion and a polar molecule. So there could be like 2 scenarios for this. There could be an anion, a negatively charged molecule, or polyatomic, or a negatively charged atom or polyatomic molecule that is attracted to a polar molecule, or a cation, which is positively charged, attracted to a polar molecule. So in these examples, there's a sodium ion that has like a generally positive charge around it, and it's attracted to the partial negative charge that the polar molecule water has. So it's attracted to like the O on it. But then if you look at the chlorine ion, it's attracted to the partial positive that's present by the hydrogens of the water molecule. So like all the hydrogens are kind of like touching it and all that. So those are the IonDipole forces. And again, these are the strongest forces of the intermolecular forces. Yeah. So the next one is hydrogen bonding. And so hydrogen bonding is the attraction between a hydrogen atom to another electronegative atom, which is generally a nitrogen, oxygen, or fluorine atom. But again, you could see hydrogen bonding in or among different electronegative atoms as long as that atom is electronegative enough, like it has sufficient electronegativity. So a common example is the hydrogen bonding between water molecules. So again, the red is the oxygens and the little white is the hydrogen, as you can see in this little diagram. So there's like a partial negative charge towards like the top, towards the oxygen, and a partial positive towards the bottom, kind of where the hydrogens are. And you can see how the hydrogens of the other molecules are attracted to the oxygen, and the hydrogen, or the oxygen is attracted to the oxygens are attracted to the hydrogens of it. So that was that. And again, I feel like that's something that everyone understands, but then after that, I always struggled with figuring out where else hydrogen bonding is, so I just thought giving more examples would be helpful for you guys too. So this was one example with ammonia, and this is where there's hydrogen bonding between hydrogen and nitrogen. So those little pink dots represent hydrogen attractive forces, and there's some more over here. And the same with acetic acid, where there's attractive forces between the hydrogen of this acetic acid molecule to the oxygen of this acetic acid molecule, and same with the side, so there's hydrogen attracted to oxygen over here. Okay. Now moving on to dipole-dipole forces. Dipole-dipole forces are attractions between two polar molecules. So like a kind of general representation of it would be a molecule that has a partial positive and partial negative on either side of it, where these, like the partial positive side is attracted to the partial negative side of another molecule, whereas the partial negative side is attracted to the partial positive side of another molecule. So that was kind of confusing, I know, it was a mouthful to say. So here's an example over here. There's HCl hydrochloric acid. So in this one, the H has the partial positive and the chlorine has the partial negative. So the chlorine is attracted to the hydrogen of this molecule, and the hydrogen is attracted to the chlorine of this molecule. So that's that attraction between the dipoles, or between the dipoles created in that dipole moment, is called the dipole-dipole reaction. Dipole-dipole attraction. So another example is with methyl cyanide. So in this diagram, it shows that there's a partial negative towards the kind of like bluish purplish side, and a partial positive towards the like whitish grayish ball side. So again, if you look at that, the purples are getting attracted to the white, and the white is getting attracted to the purple, and so on. You can see that in all of these molecules. So all of that is dipole-dipole attraction. And okay, last one, we're so close to then. And the last one is London dispersion forces. And this is the attraction between molecules due to instantaneous dipoles. And the big thing about this force is that it's present in all molecules, or in all compounds and molecules. And the reason being is in every in every atom or molecule or compound or whatever, the electrons are always constantly moving. Like they're never just standing still, or they're not moving in like specific pathways or whatever. They're like always moving around constantly, randomly. So they're always creating these like split second dipole moments that are, again, very quickly, very rapidly disappearing as well. And so in that very like split second moment that that dipole moment exists, there is some attraction between one molecule and another. So there's like two examples over here where there's helium and hydrogen. Again, we know that helium is a noble gas, doesn't really react with anything. And hydrogen is in its stable state, so again, it also just is happy by itself, so it doesn't want to react with anything. But they have London dispersion forces because as the electrons inside them are moving around, there's going to be some moment when there is a partial negative and partial positive. And that partial negative and partial positive is going to, it's kind of like a domino effect where it's going to be like making its adjacent atom or molecule also have a dipole moment. And then those two are going to be attracting to each other. But then the electrons will move out of position and then it'll go back to the stage. So I mean, same with the hydrogen molecules. So there'll be an instantaneous partial negative and partial positive. And that will cause this B, like molecule B, to also have a instantaneous dipole. And they will get attracted to each other, and then this will go back to this stage when the electrons move, and then it's like start over. It just starts over, I guess. Yeah. So if a question ever asks what forces are present in this compound, always write down London dispersion because that's present in literally everything. So you cannot get that wrong. So that was it. Thank you for watching. I hope this was helpful. If you have more questions, please contact your professor or visit us in the Math Science Center, and we'd be happy to help. Thank you.